Okay, statistics, here we go. With the beginning of chapter 4, this is an entire chapter on studying probability. And the reason we study that is so we can get a better grip on how to deal with problems like that dot plot problem from last chapter, which was really difficult, right? How many dots out of 100 are the dots you're looking for to find a probability? That's a weird problem. And in second semester, that problem's gonna get bigger. And so we got to get a handle on this probability stuff. So here you go. I started with the rock, paper, scissors tournament a couple of years ago. And clearly we can't do that because we can't even be around each other. So I'm just giving you the results from a couple of years ago. Okay. I literally did make up a tournament bracket and have a rock, paper, scissors tournament in class. And after match one, apparently we had 6 people go. It was kind of a smaller class. And I kept the percent of rock and paper and scissors that came up as we went along, right? I nerded it up pretty good. So there was after match 4, after match 8, I just kept it running total. So I guess this is the only one that really matters. Is after we had 20 matches, solid day in class, after we had 20 matches of rock, paper, scissors, 71 times rock came up, 61 times paper came up, and 52 times scissors came up. And we all know how the game works. It should be the case that the probability of rock is 1/3, and the probability of scissors is 1/3, and the probability of paper is 1/3. They should be equally likely. That's what makes that game interesting. But that's not how it got played when we played it in the classroom. It's pretty clear that we weren't as likely to go with scissors as we were to go with a rock. Paper came in right around 1/3 of the time, so we were pretty true to that one, and then we just tended to go with rock over scissors. Definition. The probability, there it is, starting the chapter off. The probability of any outcome of a chance process is a number between 0 and 1. It could be 0 and it could be 1. That describes the proportion, that's a decimal, right? The proportion of times the outcome would occur after a very large number of observations or repetitions. How often would something occur? So maybe this is supposed to be a 1/3, but maybe this is just a human feel kind of thing. People in class psychologically just go with rock more often than they do with scissors. So if you know that and you're trying to win your tournament, maybe you lean a little more towards paper to catch these rock people a little bit more often. If you know the stats, it can help you make good decisions. Know what I mean? Okay. The law of large numbers. This says that as we observe more and more repetitions of a chance process, see, random isn't what we think of conversationally as random. It's not like haphazard or just out of nowhere. Random actually is something that describes a chance process that does have a pattern in the long run. It just doesn't have a pattern in the short term. The law of large numbers says if we observe more and more repetitions and get a lot of rocks and papers and scissors, the proportion of times a specific outcome occurs approaches its probability. Random behavior isn't completely without order. Random conversation is, but random as a chance process, random behavior is something that does actually have a regular pattern, but it doesn't show up in the short term, it shows up in the long term. All right, go to page 2. And we're going to look at an example on page 264. Here we go. So, who eats breakfast? According to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. So what does that mean? Explain what the probability means in this setting. It doesn't mean that a person has a 61% chance of having breakfast. That doesn't make sense. It goes like this. If I went and interviewed tons and tons of people and kept track of how many people said yes versus how many people answered, and I turned that into a percent, it would get real close to 61%. That's the definition of probability, a description of order that only shows up after you see many observations. Part B. Does this probability say that if 100 U.S. adults were chosen at random and asked, do you eat breakfast, exactly 61 of them would say yes? That answer is hell no. I'm going to go back to what I underlined a minute ago. It approaches probability. So if you go and ask 100 people, you should be close to the truth, but you're not guaranteed that you actually land on the truth. Okay? Definition. Random in statistics, not in conversation. Random is not unrelated behavior or haphazard behavior or out of left field or out of the blue or just crazy out of nowhere. Random describes the type of order in a chance process that is unpredictable in the short term, which is why things like sports and gambling are so fun for so many people. It's completely unpredictable in the short term and anything can happen, but emerges in the long run. Things like the World Series are really fun to watch because you got great hitters. In the short term, you don't know if they're going to get the big hit or if they're not going to get the big hit. But when you're putting them on maybe your fantasy baseball team, if you're one of those kind of people, you definitely want somebody who's a great hitter because the hits emerge over the long run of a whole season. You're guaranteed almost to get lots of hits from that hitter. But in the World Series, you're not guaranteed anything, and that's why that stuff's so exciting. There are two myths about randomness, and we should address them right away. The myth of short-term regularity. See, nothing happens in the short term that's predictable. Nothing. But we can't stop ourselves. Our intuition doesn't stop us from thinking this is true. Random behavior and probability don't emerge as a pattern. As a true pattern, they don't emerge until we observe many, many trials. That's the law of large numbers from the other page right there, right? Doesn't emerge until we observe many trials. But for some reason, our brains can't accept that. Our intuition expects the odds to dominate results even with less than 10 repetitions. Now I know you're stubborn and you're thinking, I don't think that. I don't have this problem. I don't have any intuition that's stubborn and tells me that I think this is going to happen. Oh, really? Well, let me give you a multiple choice test and let me have the first 4 answers be C, and let's see how much you start freaking out in the middle of a test. You think this should be a B, a C, and a D. And if it shouldn't, it damn sure shouldn't be 4 C's in a row. That's when you start freaking out and you go, would Larson give me 4 C's in a row? He would do that just to mess with me. And now you think we're having a psychological war in the middle of your test because you're psycho, right? No, we can't stop ourselves from thinking that the long-term behavior should show up in a short run, even less than 10 repetitions. It's just something that comes up in our head. Example, which of the following is less likely to happen when flipping a quarter? Heads, 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 heads. Tails, 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 tails. I'm talking about flipping a coin 8 times. The first time heads comes up, the second time heads comes up, then heads comes up, then heads comes up, and then tails, 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 tails. Or heads, tails, heads, heads, tails, tails, heads, tails. Which one of those two is more likely to happen? The answer is both probabilities are the same. And some of you, while reading this, might have looked at that, and because your guard is up, because I already made fun of you for this, some of you are looking at that and going, you know what, Larson's up to something, I'm going to say they're the same. You might have saw right through that one. But if I ask you that question before I ask you this question, you might have had a different answer. The myth of short-term regularity is just this weird intuition that we have that says random behavior that should have a probability and a pattern should show up in the short run, and that something like this should be less likely than something else. Well, it's really not in the short term. It's not until you collect a lot of observations that you should see the regular pattern. The myth of the law of averages, this one's good. For a chance process with a fixed probability, if we see one outcome happen several times in a row, we start to think, let me underline that. It starts to creep up in our heads. It's a weird thing. We start to think that the other outcome somehow becomes more likely to happen. Right? We start to think think of somebody playing a sport. Let's go with basketball again. We got free throw shooting. You got your opponent makes a free throw, makes a second free throw, makes a third free throw. All of a sudden, your opponent's team has made 14 free throws in a row, and you foul them again. You can't help yourself from thinking he's more likely to miss this one or she's more likely to miss this one because he or she just made so many of them. It's the case that the probability is the same every time. It's just not that weird to have things happen that many times in a row. It's not as weird as you think it is. Because you think that they should even out, or I should stop saying you think. People think it's supposed to even out in the short term. It's not. The probability stays the same. One example we use a lot in this class, and I'm probably, spoiler alert, doing this for your homework or whatever. There's an example of couples that get married and then they want to have kids until they have a boy and a girl, right? They want to have both boys and girls in their family, and they're just like, we're going to keep having kids until we got both of them. And they have a girl, and then they have a girl, and then they have a girl, and then they have a girl. And they're about to have a fifth kid, and there's this feeling like that's got to be a boy because there's so many girls. But the truth is, it's a 50-50 chance every time. It doesn't have to be anything. It's a 50-50 chance every time. All right, go to the next page.